Hello everyone, this is the fourth video on the SMO Senior 2020 and we'll be going through question 16 to 20. Question 16 gives us a rather complicated looking equation. 3x minus y squared plus the square root of x plus 38 plus 14 square root x minus 11 plus the absolute value of z plus x minus y equals to 7. Find the absolute value of x plus y plus z. This looks pretty intractable immediately. There seems to be nothing we can do. We can't factorize, we can't simplify. There's really nothing that seems to pop out. But perhaps that in itself is a clue. How on earth am I supposed to take an equation like this and only have one possible value of x plus y plus z? Surely there must be something really unique about this equation that I have to make use of. Now, given an equation, we often can only work with the most complicated part of it. So 3x minus y squared and the absolute value of z plus x minus y don't really seem to hold any secrets. They are just what they look like. Whereas the square root in the middle seems a little suspicious. Is there something maybe we can do to simplify it? So let's pay attention to this middle term. Now you have a square root nested inside a square root, which means that perhaps we can try to simplify it by letting a be the square root of x minus 11, which is the nested square root. Now, based on this substitution, it means that a squared equals to x minus 11, and so x is equals to a squared plus 11. Now, based on this substitution, it would give us sorry, there shouldn't be an x down here. It should just be x, not x squared. Okay, now that should be correct. And x would be a squared plus 11 plus 38 and then 14 times of a, which is the square root of a squared plus 14a plus 49. And actually, it's pretty clear that this is a plus 7 squared, so the square root of this is just a plus 7, since a plus 7 is positive. Coincidentally, this a plus 7 is matched by 7 in the right hand side, which means that if we rewrite the whole equation again, it becomes 3x minus y squared plus square root x minus 11 plus 7, which cancels off with the 7 on the right, so I'm going to just remove it. Now immediately, this looks nicer than what we started with. But also, there is something really interesting. The square root, and the absolute value here all share a common trait, which is that these three functions are all non-negative. So the only way in which all three of them can sum to 0, and yet all of the three are non-negative, is that they are all 0. So this is 0, this is 0, and this is also 0. Now, if we substitute in x is 11 into the first equation, we get y equals to 33. We substitute both of them into the third equation, z is 22. So finally, our answer is just the absolute value of 11 plus 22 plus 33, which is 66. Next up, question 17. Suppose there are real numbers x, y, z satisfying the following equations: x plus y plus z equals to 60 and xy minus z squared equals to 900. Find the maximum possible value of the absolute value of z. Okay, so that means that z is the one that you are trying to restrict. And the restriction may not be very clear at first. Why can't z be anything I like? So let's use that to guide our thinking. So why can't z be, let's say, 100,000? Okay. Now let's see what the two equations tell us. If z were 100,000, then x plus y would be 60 minus 100,000, which is something very negative, and xy would have to be 100,000 squared plus 900, so that's a lot of zeros. And why can't they be 100,000? Well, there is quite apparently no way that you can choose x and y to get the product so big. So that means that if x plus y, you want to make the product large, and x, y are both going to be about half of this, so negative 50,000, then, sorry, that's 500,000, around negative 50,000, then x times y would be about 50,000 squared. But this here is roughly 100,000 squared. So the point of this example is to say that, you know what, z can't be that big because x plus y and xy do have some constraint. You can't just have x plus y be very small and xy be very big. So with that in mind, let's rewrite the equations first. Now the focus should be on x plus y and xy. Focus should be on x plus y and xy. And the easiest way to establish the restriction of x plus y and xy is to use this and relate it using Vieta's equation. So xy are roots of, and we can't use xyz, so let's use a as the variable this time, a squared minus 60 minus z a plus 900 plus z squared. And so, xy are roots of this quadratic equation means that there are roots. So therefore, the discriminant must be greater than or equal to 0. So that gives us now an equation in terms of z. 60 minus z squared minus 4 times of 900 plus z squared is greater than or equal to 0. We do a little bit of simplification and it would give us negative 120z minus 3z squared is greater than or equal to 0. To factorize, then the conclusion is that z is between negative 40 and 0. And so the maximum possible value of the absolute value of z is 40. So do take a moment to digest this. In order for us to find the restriction on z, we viewed it as any z I choose is a restriction on x and y. So I need to make sure I choose my z such that x and y can be found. And this led us to thinking of x and y as sum and product, and that would then give us Vieta's formulas into a quadratic. For question 18, we're asked to find this rather weird looking sum. So it's the sum from k equals to 1 to 16 of log base 2 of this rather unpleasant expression on the inside. Now, we have to kind of deal with these separately. So let's first take note that we are adding up logarithms. If we're adding up logarithms, the sum of logarithms is equals to the log of the product. Right? This is our rule of logarithms. And so we can rewrite this as the logarithm of a product. So the capital pi here is a product as compared to the capital sigma, which is a summation. Now, what goes in the bracket has not changed just yet. For us to calculate something like this, the product must somehow be nice. It's not clear why, but it surely has to be. Now, one thing we know is that this is in radians, and so k equals to 1 to 16 is a whole loop of all the values of sine around 2 pi radians, which is the whole unit circle. That means that as we go around the unit circle, some nice things are going to happen in terms of symmetry. As to which one we are going to use, well, that needs a little bit of guesswork. So the one thing that we can take note of is that this square root sine squared k pi over 8 plus 1 minus sine k pi over 8 looks like it could use a conjugate. So how would we get a conjugate? We will get a conjugate if the sine k pi over 8 got negated, while the one on the other side stayed the same. So here's what I'm going to write down. If we were to shift k forward by 8 steps, meaning k plus 8 pi over 8 plus 1 minus sine k plus 8 pi over 8. This would essentially be just adding pi. Now, as we know, when we add pi, that is going to negate sine. But when you square it, it makes no change. Whereas the one behind does not have a square, so it would change sign. Now this is the conjugate of this, and the product of those conjugates is just going to be sine squared k pi over 8 plus 1 minus sine squared k pi over 8, which is equal to 1. So that means that what we have done is to find a pairing that would give us products just equal to 1. So we pair up k equals to 1 and 9, k equals to 2 and 10, and so on until k equals to 8 and 16. Each of them would simplify into a product that is equal to 1. Therefore, the overall product is also 1. And if the overall product is also 1, then our answer is just log base 2 of 1, which is 0. So there's a healthy amount of wishful thinking that happened here. We had to hope for a way of generating the conjugate, and Thankfully, since sine is periodic, we could go halfway around the unit circle to find that counterpart, which will cancel it out. In question 19, let AB be positive real numbers where A greater than B, and suppose there exists a real number x such that log 2 of AX times log 2 of BX plus 25 equals to 0. Find the minimum possible value of A over B. This equation here is not something we can do a whole lot about, but since the focus is on there exists a real number x, let's at least open up the logarithms to isolate log base 2 of x. So this is the first. This is the second. Now the eagle-eyed among you would realize that this is actually a quadratic equation where the variable is now log base 2 of x. And saying that there exists a real number x is the same as saying there exists a log base 2 of x. Since x can't be negative, otherwise the equation would not even be defined in the first place. So therefore, we can write this in our usual quadratic equation form. When, again, as emphasized, the variable is not log base 2 of A or log base 2 of B. The variable is log base 2 of x, since A and B are just unknown constants. So in this quadratic equation, if there exists a solution, it means that the discriminant is greater than or equal to 0 again. So let's write it down. The discriminant is log 2a plus log 2b squared minus 4 times of log base 2a log base 2b plus 25. And this should be greater than or equals to 0. If we simplify this, we get log base 2 of a squared plus 2 times log 2a log 2b. However, there is a minus 4. So minus 2 log 2a log 2b plus log 2b squared minus 100 is greater than or equals to 0. And it's pretty clear that this would become the difference of logarithms. Which is none other than log base 2 of a over b. Since a is greater than b, it means that log base 2 of a over b should be positive. Therefore, log base 2 of a over b can be said as greater than or equals to 10. So a over b has minimum value 2 to the power of 10, which is 1024. Finally, let's look at question 20. We have a rectangle ABCD, the diagonal AC has length 20, and the length of BP is 15. Now P is a point on the side CD such that they are perpendicular, and we are just asked to find the area of the whole rectangle. Now this figure is full of right angles everywhere. And when a figure is full of right angles, lots of right angles, I should put that in writing, there are two things that could potentially be useful. One is Pythagoras, and the other is similar triangles. Now, Pythagoras is probably something I do not need to elaborate on, since right angle triangles mean Pythagoras theorem holds. But what do I mean by similar triangles? Well, let's do a little bit of angle chasing. If this angle is marked as theta, and this is 90 minus theta, then using this right angled triangle, angle CAB is also theta, angle ACB is also 90 degrees minus theta, angle ACD is also theta, angle CPB is also 90 degrees minus theta, and angle CDA is also 90 degrees minus theta. And that means that all the right angled triangles in this figure are similar to each other. Since all the right angled triangles are similar to each other, a pair of lengths like 20 and 15 is already really powerful. Now let's call this point X. Now we know that XA is to XB would be equal to XC is to XP because of the pair of similar triangles. And we know that XA plus XC is 20, since that's the diagonal AC, while XB plus XP is the diagonal BP, so that's 15. And so it means that the ratio of the sums is 4:3. And since XA to XB and XC to XP are in the same ratio, it means that they are also in that ratio 4:3. And that means that literally everything in this triangle is a 3, 4, 5 triangle. So every triangle is 3, 4, 5 in this figure. So since every triangle is 3, 4, 5, then we are basically done. So AB would be 4/5 of AC, which is 16. Meanwhile, BC would be 4/5 of BP, and that is equal to 12. Hence the area is just 12 times 16 equals to 192 cm squared. As it turned out, we didn't need Pythagoras at all, except for the fact that the ratio is 3:4 implies the hypotenuse is in the way of a 3, 4, 5 right angled triangle. Alright, that brings us to the end of this video, and in our last video, we will be looking at questions 21 through 25.